All right. Okay, buckle up. The future is wide. The year is 2017. Moore's law is dead, or at least the various misinterpretations around Moore's law and getting a CPU twice as fast every 18 months for half the price, or whatever it is, those days are gone. But this presents some interesting challenges. The future is wide. How wide? Well, here's the state of the art in 2007, 10 years ago. So this is a 4-core processor. It was 128 bits wide in terms of its vector units. That is to say it can process 4 32-bit floating point numbers at a time. In 2017, well, you can see in terms of clock speed, it's not a lot faster. It's got more cores. It's got about 4 times as many cores, but it's much, much wider. In fact, it's actually wider in terms of SIMD lanes than this auditorium is wide. So that's pretty wide. On mobile, that's the original iPhone. 10 years on, it looks kind of the same. It's a little bit bigger on the outside, somewhat faster on the inside, and much, much wider on the inside, whereas the original phone could do maybe 1 floating point multiply each clock. This one can do up to 12. But taking advantage of all of this, unfortunately, doesn't come for free. There is no such thing as a free lunch anymore, unless you work at ROLI, in which case there is a free lunch every day. It's excellent. I highly recommend it. So yeah, come and work for ROLI and enjoy the free lunch. Unfortunately, it won't make your code run any faster. So let's look at how to do that. Before we deep dive into the architecture itself, I want to recap on some of the key concepts around parallelism, which is a really tricky word to say, and unfortunately I had to say it rather a lot in this talk. Here we go with the kind of 4 levels of parallelism, which is system level. You can think of that as clusters. Thread level, think of that in terms of the different cores or the different sockets in a single system. And then instruction and data level. Now, when we think about system level, you can have some completely different tasks. You can even have different kinds of chips running in your system. When you think about a CPU and a GPU running their own kind of full stack operating systems, that's system level parallelism. Hasn't really caught on for audio work because the sort of synchronization quantum, the minimum task size for that, is pretty big. You know, if something's got 100 milliseconds of round trip latency to synchronize, that's not much use when you're running 3 millisecond audio buffers. Thread level parallelism, that is used quite a lot in audio, but it's mostly managed by the host and the operating system. It can run a bunch of quite different tasks, but the sync quantum there means you can't write really tightly optimized audio code just by multi-threading. Instruction and data level parallelism, that is what we're going to be interested in, and those are running on much, much finer grained tasks and sort of synchronization quantums on the nanosecond order. So this is sort of 10,000 to kind of 10,000 to 1,000,000 times finer grained. We're right down at the micro level, but what you can see there is that your tasks have to be very closely coordinated. At instruction level, you can be doing some things that are sort of a little bit different, maybe different parts of the same bit of code, and once we get down to data level parallelism, you have to be doing exactly the same thing to all your parallel lanes. Now, in the audio world, we mostly want to write once and run everywhere. You know, when you think about game engines, they can afford to hand optimize for different architectures, different use cases, in some cases sort of different generations of the same GPU architecture. We probably don't have that luxury, and there is a lot of everywhere. These are some of the popular architectures, and even those using the same instruction sets will actually have radically different characteristics when it comes to what's most optimized for a given platform. Even on one particular platform, there are a whole lot of variables that can affect how your code performs at runtime, from thermals and power to the state of the cache. If you're writing, say, plug-in audio code, you're sharing the chip with a bunch of different code from a bunch of vendors. It may have different characteristics at different times, so there are lots of things that can influence how your code performs. So we're gonna dive in and look just at these two on the right, instruction and data level parallelism. If we think about a digital audio workstation, a host, it's kind of modeling what goes on in a studio. So here's where you can find some parallelism within that studio. You can see we've got a bunch of big things spread around this room, and those you can think of as tasks that you might split out and run in different threads and different cores. We've got some samplers there, we've got a mixer, we've got a guitar, some synths. Those are all good candidates to be broken up into threads. But we can also find some parallelism down at a finer level when you look at, say, this vintage synth at the top left there, or a circuit board from another old Oberheim, or the mixing console, or indeed the piano with its 88 notes, each with their own sets of strings. Those are all things that are happening in parallel, and it would be nice to find a way to exploit that efficiently. Before we dive further into this, I want to quickly explain instruction latency. Now, hands up who already understands instruction latency. Some of you. Okay, now this is not audio latency. This is a similar problem, but operating on a much, much finer scale. If we look at some very simple filter code, this is like the IIR for dummies. We can compile that, and if we compile it for an SSE machine, an Intel, sort of older generation Intel machine, this is the assembly code we get out. Now, a typical Intel chip can do one load or store, or one load, one store, and a couple of multiplies or adds per clock cycle. So how long does this code, which has got two loads, two multiplies, an add and a store, how long will that take to execute? Well, the answer is longer than you think. And the reason for that is that all of these operations have some internal latency. What we can see here is that those two multiplies, which also have a load in them, they have to fetch some data from memory as well as multiplying by a register. Those can both start executing on clock 0. We're using zero-based counting here. We're all programmers, right? But then the add that immediately follows them can't actually start until until clock cycle 7 because there's latency there both on the level 1 cache and in the multiplier. And this is a kind of best case where we actually hit the L1 cache. Sorry, did you have a question? Sorry. Okay. Yeah, and if we have to go to level 2 or worse yet, main memory, well, that can be in some cases hundreds of cycles. So please look after your cache, because if you hit main memory, it's terribly, terribly slow. So what we can see is that our wonderfully fast CPU is actually sitting there doing nothing for 6 cycles, waiting for more data. Now, a quick way to fix some of this is to interleave. So let's say we're writing our IIR for dummies in stereo. We can actually interleave code from 2 separate audio channels. And because there's no data dependencies between those two things, it's now basically able to run the code for the right channel while it's waiting for things to complete on the left channel. And in this example, we're able to do twice the work in just one more clock cycle by interleaving 2 ways. But there's a kind of Goldilocks zone for interleaving. If we do too little, you get these bubbles, these gaps where the CPU pipeline isn't doing anything. The CPU is waiting for previous instructions to complete, and the processor stalls waiting for the results. On the other hand, too much. A microprocessor only has a certain number of visible registers. That varies from one architecture to another, and it's even different depending on whether you're running in 32 or 64-bit mode in some cases. And you end up churning the register file. You end up having to constantly send data back to memory and fetch it again. And that can be expensive, and then your CPU will stall waiting for the cache. And unfortunately, it's really difficult to determine for any given algorithm what the optimal interleave for that will be, because of the register file size, because instruction latency varies depending on which CPU you're on. Different cores can issue different numbers of instructions on any one clock. Cache latency, bandwidth, all of these things vary. And also compilers will actually they'll do a pretty good job trying to make the best job of this. But each compiler will behave somewhat differently in this respect. So that can be challenging. I'd also like to quickly recap on what SIMD is: single instruction, one instruction, multiple data, more than one data stream. It does this. It will, in a single add instruction, so that's one instruction for the processor, is actually working on 4 sets of numbers, 4 pairs in this case, at once, executing in one clock cycle, although not necessarily, like I say, not necessarily completing. You may have to wait for the result, but it's only one tick to fire it off. Unfortunately, there's a lot of different varieties of this, so we can look at, these are kind of all, or mostly processors in somewhat common use today. So that's 5 different instruction sets, each with a couple of different sub-flavors or feature sets that may or may not be supported on any given processor, different widths, different issue widths, and some have some special features like this FMA, which stands for Fused Multiply Add, which is a multiply and an add in one instruction. So I set out a few years ago to solve this in a way that would exploit this parallelism that's there, waiting for us in the studio, but could be generalized in a sort of write once, run everywhere type of approach, and still run reasonably optimally, not as good as hand optimizing for every possible target, but I don't have time to do that, and I doubt any of you do either. So this is kind of a way to get almost the best of all worlds, at least that's the plan. We want to write code that looks like DSP code. If you've ever seen handwritten assembler like machine intrinsics, it's not the most readable code when you implement, say, a big IIR filter using those intrinsics. It can go pretty fast, but it's not very maintainable, and like I say, you have to rewrite it each time. So we want to write once and let the compiler and the system do the rest of the work. And that's what this sets out to do. So I'm going to give you a sort of whistle-stop tour of the system. I'll be posting a GitHub link a bit later on, and I really encourage everyone to download this code and play with it for yourselves, explore it and see what you can do with it, and maybe you'll find some uses for it that I haven't even discovered. The code on GitHub is very much a demo, not a library. It's not supposed to be production grade, and it's missing a few things that you might need to really use this effectively in practice, but you can see at least the speed ups and figure out what you can and can't do with it. There are a few other caveats there. Not all code lends itself to this approach. If you have system calls, if you have some transcendental maths that don't have a decent numerical approximation, if it's very memory intensive, if it's kind of branchy and can't be made unbranchy, or if you're targeting one specific system. But with those caveats, let's go on and take a look at the parts of the system. So we start off with an interleaver. Now what this will do is take a single stream of code and generate an interleaved multi-channel version of that code. The idea being here we have a function, like a code generator that takes a 2-operand function, unrolls it with a simple for loop at compile time. So that interleave is a compile time constant. So that should be nice and fast and nice and clean. We can write one multiply instruction and get an interleaved one, right? Well, almost. It turns out there is one very popular compiler on the market made by a little company called Microsoft that doesn't understand compile time for loops when you use SIMD intrinsics. So instead we end up with this not terribly pretty compile time if statement. The important thing to take away from this, though, is this isn't branch-intensive iffy code after it's been compiled. So this interleave template parameter gets evaluated at compile time, and so it'll generate only the code that it needs to generate for the particular interleaving it needs at that specific line. So we then have some wrappers around that to give us the sort of standard maths operations, assign, add, subtract, multiply, etc., and some compare instructions as well there. And this gets passed up to a machine-specific SIMD implementation. So we have one implementation class for each of the instruction sets that this library targets, which is scalar floating point, SSE 2 through 4.1, AVX 1 and 2 on some of the newer Intel processors, AVX 512, which is Intel's latest and greatest. If you go out and buy one of the new i7s or i9s, that may have this instruction set on it, and then the Neon instructions used on ARM. So you'll find, as you take a look at the code, you'll find sort of machine-specific implementations there. The architecture's built around a sort of node and voice system for being sort of signal processing code. If we think of this in the synth context, you might have your oscillator, which is connected to your filter, which is connected to your amplifier, and then each of those would have an array of active voices, which are kind of the voices of your synth. So you can think about a sort of graph walking algorithm that will hop around those nodes and then call each of the voices to process. That has your sort of standard goes inters and goes outers, so you have kind of audio buffers in and out. You have some control rate parameters, so kind of things that only update once per block cycle. That might be your cutoff and resonance. And then within the voices, those would have some member variables that might be sort of filter memory state, or that might be pre-computed coefficients, or those kinds of nuts and bolts. We have an input-output adapter class, and what this does is to make the DSP code, which is sort of the top layer. It's where we want to spend most of our time, is actually writing DSP code, oscillators, filters, envelopes, rather than thinking about this machine-specific stuff. And this just lets us write that code in a way that is independent of the memory layout, independent, hopefully, of all the stuff going on underneath. So we can change memory layouts, try different interleaving factors, try different voice configurations without affecting the DSP code or sacrificing performance. And what this is really doing is taking the voices, which are, if you like, an array of structures, and transforming that data into the structure of arrays needed by the various vector processors, and that will handle all of those things. So when we finally get to write some DSP code on top of this, we end up with something like this. So this is kind of your declaration for a very basic linear amplifier. If those of you who are familiar with the VST SDK, this is kind of the gain plugin, the hello world of audio DSP architectures. So that's really just boilerplate declaring the ins and outs. And here is the processing code, which rather than living in a voice or a node class, this is wrapped inside a templated worker type, which takes an input-output adapter and will basically use the types supplied by that input-output adapter at compile time to generate the actual implementation of our processing code. So you can see there at the bottom we've got effectively an inner loop there where we're reading a sample, multiplying it by a linear gain and sending it to the output. But what this is doing there is we have this interleaved type which is n ways interleaved and m lanes wide, whatever is the best for the architecture it's running on, and that innocuous little multiply symbol, that can be many different things depending on where we're running. Finally, we have a dispatcher, and the job of the dispatcher, and the one provided in this library is kind of a bit of a dummy, but the job of this is to work out what architecture we're on and dispatch to the right code to do the job. And last but not least, as you have a look around the library, you'll find a couple of stopwatch and benchmarking classes, which are really just little helper utilities to tell us how fast things are going. So when we put it all together, we can instantiate all of this stuff into a concrete implementation there. And this example here is for the AVX instruction set and that basic amplifier example that you just seen. So this is basically generating the processing code for that specific combination of a machine architecture and a set of DSP code. The idea being that this is simple and dumb enough that we can generate these sort of cookie cutter compilation units with a script in scripting language of your choice. And this is really where the magic happens. We have a DSP class, which is our basic amplifier. There's the type of node that goes with that. And then we are creating a worker for that DSP class and for that specific instruction set, and basically calling that, telling it to process all the active voices. And that one line of code will instantiate thousands, which is kind of the magic of C++ templates. So does this actually work? Let's take a look, see what it does. That is the GitHub link for the code. I highly encourage you to get a hold of that, check it out, do send me any feedback, tell me why my coding standards are non-existent and terrible, etc. This is the test system that most of these tests were done on. There's a few other things thrown in there as well, which I'll get to. So it's a fairly recent, but kind of old enough to be widespread laptop. And here's some results from the basic amplifier. Well, that's not too bad. I mean, this basic amplifier is such a trivial piece of code, you probably wouldn't go to the trouble of building all of this architecture just to support a linear gain amplifier. And in fact, that's something that's so dumb you probably could spend the time to hand optimize it. Nevertheless, it's kind of gratifying to see that we've resolved down to some really kind of sane and simple assembly code there. And we're getting a nearly 12 times speed up by going to 8-way interleaved for 64 voices and using that AVX vector instruction set. So that's not too bad, 12 times speed up on that. But I actually cheated a little bit here, and I hobbled the compiler, because modern compilers are very smart, and actually the latest Clang compiler will do a pretty good job of auto-vectorizing that very trivial example code. So what you can see here is that the Clang compiler, with the kind of hobbles taken off, it's actually taken our 16-way floating point code and sped that up to be within 50% of our very cleverly template optimized AVX implementation. If we were working with a constant block size, there are other things the compiler can do as well, but this code is written for variable block lengths, so that limits a little bit. Next up, we've got a panoramp. So this is still pretty basic, doesn't do that much. Here's how it performs with the compiler allowed to do its thing. And again, although we get a very big speed up, 14 times faster than scalar code, and I think the 4-way interleaved is actually faster in this instance. The 4-way in this one is more efficient than the 8 because of register spills. But again, the compiler does a pretty good job of catching us when we do interleave basic floating point code 16 ways. One band EQ. So this is slightly different now because an EQ being an IR filter, it has some internal feedback, and this means that some of the compiler's strategies aren't available anymore in terms of it auto vectorizing. Here's the one band EQ example. This is actually a templated IR EQ as well, so you can actually instantiate this with different numbers of bands. This is resolved at compile time to a one band version. And here's what happens at a few different block sizes. So those of you familiar with audio processing code will know that normally the larger your block size, the more efficiently the code runs. And here that's true up to a point. And you can see that 256 samples, we're spending a lot less time gathering state, scattering it back to memory. We're spending a lot less time computing coefficients. And the two-way code there gets a 13-fold speed up. When we go to 1024 samples, things get slower again. And yet, the 8-way code is now faster than the 2-way. What's going on here? Well, 1024 samples times 64 voices is simply too big to fit in the cache of the chip we're testing this on. The bigger buffers means we're hitting level 2, level 3 in main memory more often. So the 8-way interleave, which does more in the way of latency hiding, even though it's less efficient in terms of register use, that actually wins out as you go to this bigger buffer size. But other algorithms will be affected differently by this, so we don't necessarily know ahead of time how any given algorithm will perform. It's why it's nice to have all the options there. Similarly, with the N-band EQ, we're back at 64 samples, but you can see how the relative performance of these things changes as you go from 1 to 2 to 4 bands, simply because those become more kind of data intensive. These have all been pretty trivial algorithms so far, so now I'm going to move on to something a bit bigger. This is an analog modeled ladder filter. This is based on what you get in F-Expansion's Strobe 2. It's a fairly chunky piece of filter code. There's a lot going on there. And if we look at this with IACA, the Intel Architecture Code Analyzer, which is a great little tool if you like sort of digging around in this stuff and understanding what's going on, it tells us that the block throughput on this one is 225 cycles, whether that's serial or vectorized code. Mobile is obviously important as well as desktop, so let's see how this goes on some ARM processors. There's a Raspberry Pi on the left there, Raspberry Pi 3. Those don't really have great vector units on, so it's speeding up by a bit over a factor of 2, so that's still not too bad. But you're seeing much bigger benefits on these slightly bigger and wider chips. So this A57 on the right here, that's what you would have got in a high-end phone a couple of years ago. Looking at some higher-end ARM processors, they're somewhat faster on the scalar code there. I mean, this A11, so this is the iPhone X on the far right there. It's a bit faster. It's like 3 or 4 times faster than the Raspberry Pi on scalar code, but it's when you start to run wide code on it, you really get the benefits of the wide architecture that's in that A11, and it's actually able to run 15 times faster than scalar code. So this is using a 4-wide vector that's been 8-way interleaved, and you get a very, very big speed up there. So it's a 15 times speed up using this approach on this kind of fairly big filter code. Over on desktop, on Intel architectures, again, we can see a similar pattern. Don't buy an Atom to do audio processing on, at least not this kind of audio processing. We've got Core 2 there. That was a state-of-the-art machine 10 years ago. That's my old Mac Pro, which is on this benchmark a third as fast as a phone. Oh dear, poor old thing. And then you can see with the more recent architectures, you can see again these bigger speed ups. These have this 8-wide AVX architecture, which can do obviously twice as much work in ideal conditions per clock, and you can see that this is really scaling quite nicely with that. And then lastly, we've got a machine from the future, or at least from the Google Cloud, and this is one of the machines with the new 512-bit vectors on there, and we're able to get a 32x speed up versus scalar code. So this is really well worth doing if you want to be able to kind of take advantage of those sort of features. Now, we see across a lot of these graphs that actually 4 times seems to be the winner a lot of the time, so why not just interleave 4 ways and forget about the rest? Well, we don't always need to do 16 or 32 voices worth of work, and although the relative efficiency of of 1 way is lower than 4, in absolute terms, if you're doing less work, even if you're doing it slightly less efficiently, you're still doing less overall. So say you've got a synth with dynamic voice allocation, or a mixer with that adapts its number of channels. You don't want to have to stick with 16 or 32 voices when you only need to process 4. And also this example is just one algorithm, and it would be hard to know at the time that you're writing that algorithm whether 4 times is going to be the quickest. It's a difficult thing to sort of reason about. So yeah, it's nice to be able to write your algorithm independent of your interleaving factor, your machine instruction set, and just pick the winners after you've compiled it and run it. So far, we've been looking at how this works for various kind of filters and gain amps. Let's see how to do this for an oscillator. Now, oscillators, particularly analog model oscillators and samplers, present some unique challenges because they tend to have branches. But in order to run in parallel, all of this code has to follow the same instruction tree. So if statements are banned here, we need to go branchless. Fortunately, we have conditional masks which can help us with this, and here's how they work. So what this is doing is basically carrying out a comparison between 2 sets of values, and that comparison creates a mask. And what you can see here is where the comparison result is true, it will set all the bits in the mask to 1, and where it's false, it will set all of those bits to 0. And then we can just do a logical AND with that mask and just get values for the sort of if true case. Or so you get a value for if true, you get a 0 for if false, and that lets us build a naive sawtooth oscillator. Here's kind of the example code for how you'd do that. I hope that's kind of simple enough that everyone gets it. But hands up who likes the audio from a naive sawtooth oscillator? Anybody? No, didn't think so. These things sound terrible, so we need to band limit and avoid aliasing. Now, typically what you do here is you have what's called a band-limited step function, which is smoothing the edge on that sawtooth wave transition to make it band-limited. And usually that's done with if statements. When I sort of inherited this synth engine, it came with a MINBLEP, which is a minimum phase band-limited step oscillator. It's quite a well-trodden path there. They're reasonably efficient. They're easy to reason about. They sound good. They don't really have any DC artifacts, unlike some oscillator algorithms, and they survive modulation reasonably well. They don't blow up, which is also nice. However, they have some nasty kind of architectural implementations. If you're trying to write sample-by-sample audio code, they inherently have side effects ahead and behind of the current, if you like, playhead. They're inherently branchy. They depend on if statements, which makes them difficult to vectorize efficiently. They're somewhat memory intensive, and memory is slow. Main memory is very, very slow, sometimes over 100 cycles of wait if you miss the cache. And even if you just use a lot of memory locally and make the cache more polluted, less efficient, that can kind of drag performance down of everything across the board while not necessarily showing up obviously in a profiler. So it can be quite a sort of insidious performance degradation there. The thing I really don't like with this algorithm is that the efficiency varies with your audio frequency. So what this is doing is, depending on how high a frequency your audio is running at a high frequency, you're going to have more of these step transitions, you're going to have more branch mispredicts, you're going to be doing more of these memory-intensive band-limited steps to fix up the non-band-limited naive waveform. Let's try and come up with something better. We want something that's high performance, can parallelize well, no ifs, using simple primitives that are widely available. You don't want expensive coefficients. You still want something you can understand. You want something that sounds good and still doesn't have DC and can survive modulation. So I looked at an algorithm called the Polyblip, which some of you will be familiar with, which is the polynomial band-limited step. We've still got we've got actually 3 branches there, 3 if statements. That's not ideal. And then also some divides, which again are slow. If you can do multiplies or adds or pre-compute an inverse instead of doing a divide, that can save you a lot of time on the processor. And because of these if statements, the compiler won't be able to do a very good job generally of auto-vectorizing this sort of simple bit up at the top. You know, most of the time you'll actually miss those if statements, but because they're there, most compilers, I hesitate to say the compiler can't do it, because compilers are very, very smart and they keep getting smarter, but typically it won't be able to do a linear auto-vectorization on this code. But fortunately, we can rewrite this branchlessly, and there's a kind of visualization of what that's doing in a fairly crude way on the right there. We have the simple kind of naive phase increment running -1 to +1. We then can generate some kind of windowed windowed shapes off of that we can then shape with a simple quadratic polynomial. There are much better polynomials available than this for doing this polyblip job, but this one is really kind of straightforward and easy to understand, and it actually sounds 2 times oversampled. It actually sounds pretty good. It's not perfect, but most of that aliasing is kind of down below the 16-bit noise floor. That's pretty good quality, and obviously the more we oversample, the better that gets. And I think we can afford to oversample, looking at some of the speed ups we get here. So that's 25 times speed up. I think we can maybe oversample that a bit. And yet there's something not quite right with these numbers. It's not scaling up quite the way it should. You can see that the AVX 512 there is only sort of a fraction faster than the 256-bit, which is doing 8 numbers at a time. This one should be doing 16, should be a lot quicker. So I dug in with the that IACA tool, took a look at what was going on, and it turned out that this compare and subtract that it does actually isn't super efficient on AVX 512, and Intel have changed a little bit how this instruction works, how this way of doing things works as they went to 512-bit. But we can now get a compare, basically a compare, a mask, and a subtract down to 2 operations just by retuning that a little bit. And we get a slightly better speed up there, but the numbers still don't look quite right. In particular, that 128-bit code looks faster than it should be. So that's before. That's before. That's with the fixed compare and subtract. It turns out the compiler is actually cheating a bit. If we look at the command line there, what it's actually doing is generating some 512-bit code using 32 registers, even when we're only using the 128-bit intrinsics. So if we actually set the compiler to build for the architectures that we're really targeting here, and this is still benchmarking it on the same system, but this is now basically preventing it from generating instructions that wouldn't be allowed on a 128 or a 256-bit architecture, and now we can see more or less the scaling that you would expect from that. So this 64 voice example, if we run it at 96K, so that's the kind of 2x-ish oversampled, we're getting 64 voices of that for 0.13% of the CPU on 1 core. So I think that's reasonably efficient. So please download the code, have a play with it, see what you can do with it. If you come up with anything that I haven't thought of, drop me a line. I've got a couple of sort of future projects for this code, which I didn't have time to get to for this, but I think are directions worth exploring. First one is a latency hiding sampler. Like I say, memory is slow, and if you write a sample playback synth, then it would be really nice to be able to hide the hundreds of instructions it's probably going to take to fetch 64 voices of samples from main memory. I have a way to explore doing that. I'll let you know how that goes. And then also extending this architecture to support thread level as well as the instruction and data level parallelism, so that we can take generic DSP code and span it across multiple small cores. You don't need to do this on an i7 or an iPhone 10, but if you're trying to, say, run some high-quality code on a Raspberry Pi, you've got 4 fairly tiny cores there, so being able to span that across a couple of threads without having to worry about things like cache coherency and memory models would be nice. And that's pretty much it. Like I say, download the code, do have a go with it. Some useful tools I found while working on this, which I thought I would share. The Intel Architecture Code Analyzer, yeah, like I say, great for poking around this stuff. It's kind of a static analyzer for compiled assembly code, and it'll tell you for any given architecture on a really fine level, you know, where it's hitting and where it's missing. Termux and the Hacker's Keyboard. I was doing a lot of profiling on Android devices. The Android dev toolchain is not always the nicest thing to work with. This lets you run Clang and GCC actually on your phone, which is kind of fun, compiling little projects on a phone or a tablet. The Google Compute Cloud, thanks to which I was able to test this stuff out on CPUs that at the time you couldn't even buy yet. Thank you for that, Google. You can buy them now. I think my old Mac Pro there is slower than a phone, poor thing. Yeah. And you need a good profiler if you're going to do this stuff. And then finally, Compiler Explorer. This is a fantastic, useful little website which Jolt, who some of you will have seen give a talk yesterday, he put me onto that one. Thank you, Jolt, because this lets you explore what kind of assembly code is generated from all the different compilers. It has some restrictions, and you'll see in my library there's a kind of special compile for that, but it basically lets you explore, is this compiling sanely on GCC, Clang, ARM, x86, x64, just by kind of ticking drop-downs on a menu instead of firing up a whole different machine. So well worth it. And then finally, if you want to understand what's going on inside all of these CPUs and what they can all do, I recommend the websites below, especially Agna Fogg, who compiles tables of instruction latencies for every single architecture. It's an incredibly useful resource, and long may he keep doing it. Thank you very much.
Thank you very much, Angus. We have a few moments. For questions, and please do not ask your question until the microphone is in front of you, because we're recording all this.
Okay, thank you. So, how do you distribute your code if it's compiled for such specific different instruction sets or different capacities of machines?
So it's provided it's one compilation unit per architecture, or provided you don't mix different architectures in one compilation unit, you're actually safe on that front. So you need to make sure that the right flags are set for your specific compilation unit. So what you typically do is compile the vast majority of your program, where it doesn't have to be fast, for the sort of lowest common denominator instruction sets, and then your sort of highly optimized kind of concrete instances that you get out of this. You say, okay, I'm going to compile an instance for AVX, an instance for SSE, etc., and then the dispatcher, which is again compiled as sort of lowest common denominator code, will then be calling static functions in those compilation units, but it will only call that on the supported processors. So you can ship one binary with a dozen different architectures in it, and that's not a problem.
Thank you.
Oh, thanks for that, Angus. That was really awesome. Have you thought about doing something similar on a single audio stream, processing it horizontally using SIMD?
I mean, that's certainly something you can do. I think the Juice DSP library has some primitives for doing that sort of serial vectorization. By and large, I mean, it's worth doing in a lot of cases. It's not as interesting a problem to solve. But yeah, I mean, being able to multiply a horizontal, like a 16 samples, and just abstract that across a few architectures it's worth doing. But there are some cases where you can't, like this, the if statements in that BLEP oscillator. It will kind of hit a wall at an if statement, and I mean, actually, compilers do a pretty good job of doing that for you. So if you have compilation units for the different architectures and a dispatcher, you could do that without any intrinsics, any clever stuff at all. You could just have a copy of your filter or oscillator, one compiled for SSE, one compiled for AVX. Let the compiler do the work on auto-vectorizing, and then just dispatch to that would be the kind of cheats way of doing that.
Hi, João here. I'm really addicted to fixed point arithmetics.
Mm-hmm.
Should I expect the same results using wide registers on fixed point DSP?
That's a good question. I haven't done much with fixed point on these architectures. You do have integer. Operations. Not in this particular library. This doesn't have the integer intrinsics in it, but those exist across SSE, AVX, ARM, all of those things.
Yes.
So you can follow the same pattern with integers, and that would probably work for that, I should think.
Yeah, I have done a lot of wide integer multiplication with it, but I couldn't do like this detailed branch marking. But it's a lot faster.
I'm sure.
Especially when you're doing multiply accumulate operations.
Yes.
And I do a lot of filters with noise shaping in it. And it works especially well when you're doing noise shaping because you can keep very large results from accumulations.
Okay.
But I would really like to try to add some fixed point things to this code of yours.
Okay, I mean, by all means, do check it out and
that was a volunteer.
And send me a pull request when you got that figured out.
I'm going to allow one more question from this side because I've been very unfair. One more question? Anyone over here?
Right.
So are there any rules we can follow when we decide to optimize ourselves, or we let the compiler do, or always we need to try to know exactly which one is better, more efficient?
In terms of this architecture, because there are so many different systems, and even the performance of those individual systems can vary depending on buffer size, this approach is try lots, profile lots, and just pick the winners. Potentially, I mean, I haven't actually taken it quite this far, but potentially you could actually profile at runtime, you know, optimize the system at runtime, say, okay, based on what's going on now, which instance of the algorithm is actually performing best, and let's switch to using that one. I haven't taken it quite to that point. It only optimizes based on the number of active voices and the best available instruction sets. But yeah, you could do that at runtime quite easily.
Thank you.
We need to wrap it up here to let the next session start. So let's thank Angus once more.